Hi Molly, can you show me your face?
Recording in progress.
Do you have any particular question?
Okay, can you hear me?
Oh yeah,
Okay, I did make it to the meeting. Sorry, I'm trying to figure out Zoom. I am awful with some technology.
no problem. Just let me know. I can even go to your problem there. Do you have any particular question or
I'm
problem?
do my homework right now. I do have some that I didn't quite get all my homework done yet, but I did not. I could use definitely some help with.
Mhm.
Off the top of, well, let me see.
I can even bring yours here too. So let me.
It says, I don't know. Mine's just like a picture. Okay. Anyways, okay. On the question,
Maybe question 4.
the
So start from question 4.
yes.
Okay. So I actually copied and pasted similar question. It's a little bit different from yours, but basic concept is the same. So I will share my screen with you.
Okay.
I think I am already sharing it, right?
Yes.
Okay, so it's very similar, just maybe the starting number, the price should be different. Okay, so this question is saying a certain game show distributes prizes that are powers of 2. So they are using only powers of 2. For example, powers of 2, 2 to the 0th power is 1. So let me use my pen here. So that $1 is the same as, oh, it's not connected. Hold on. Okay, now I think it is. 2 to the 0th power is 1, so that's $1. 2 is 2 to the 1's power, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the 4th. So all of these numbers are power of 2, 2 to the 5th, 2 to the 6th, and so on, right? So 512 is what? 7, 8, 9, 2 to the 9th power. 6, 7, 8, 9, right? Okay. So these are the powers of 2, and this person wants to give away the prizes with only power of 2. So at least one prizes per each we want to give it away. So when you're starting giving away, you're gonna start from the big number, from $972. So we can give away 512 from 972. How many of them? Just one. Give away just one, because that's the minimum number. Then how much is left? You can just subtract 512 from 972. I can use my calculator and I get 460. So I have 972 minus 512. After giving that one ticket away, I have $460 left. So can I still give away $256 ticket too? I have enough, right?
Yeah.
So I can give away one of that price from 460. If I give away $256, how much is left? 204 is left. So can I give away $128 ticket? Yes, I can, right? I have enough. So that's what you're doing.
Makes more sense now. I just needed someone to explain that to me. I didn't.
Yeah. It didn't make sense. Yeah, it didn't have any explanation further. So you can just keep doing that. Then let's do a little bit more. Okay, $76 is left. So we can give away $64 from $76 too, right? We have enough money. So we can use one ticket for that. then I can use 64 out of 76 and I have $12, right?
Yes.
That's not enough for $32 ticket, so I cannot give away any of them. That's why it's 0,
Okay.
right? And
Yep.
$16 ticket, I still cannot give that away because I have only $12 left, so 0 for that. But yes, I can give away $8 ticket, just one of them. So I can give away $8 ticket. Then how much is left? I have $4 left. So I can use that one. But after using that $4, I have no more money left.
Right.
So the rest of them is 0. So does it make sense?
Yes, it makes total sense.
Okay, great. That was my first question here too, and probably you have question on this one too.
What question was that? 5?
Everybody has a different number for this one, so I'm not so sure which one it is on yours.
Oh, yes, that one definitely.
Yeah, I think a lot of students made a mistake on this or they were struggling with it. So let me explain on this one. So, interpretation of this one, this is cardinality. So how many are there in set A, right? So we have 2 sets, set A and B. Usually we use a Venn diagram like set A and set B, right?
Right.
And that's the total set, universal set. Then it says set A, number of elements in set A. So all of this together, if I use color there, number of elements in set A is 5, right? That's what it says here. So that is 5. There are 5 elements, whatever it is. It can be 1, 2, 3, 4, 5. It can be A, B, C, D, E. It can be something else, right? Anyways, we don't know what it is, but there are 5 elements in set A. And we are also given union of A and B. What is union? Union is A or B. So we are talking about A union B as everything here, A and B, A or B. So A union B, let me rewrite that. If A is B here and B is there, then this is A union B. And if we have this part only, that's intersection of A and B. Okay? So if we know that, everything gets easier because it says number of elements in A union B is 8. So together, this part and that part together has to be 8. Then definitely we know that this part here, the white part here in B is 3. But do we know how many we have in this intersection part? We don't, right? But we definitely know that. This part does not exceed 5 because the total number here and that together is 5. So we know that A intersection B does not exceed 5. So it can go up to 5. Does it make sense? Okay.
Yes.
So we can think about what if A union and intersection B, so I'm talking about this part here, that's A intersection B, it cannot exceed 5 because this total is 5, right? So it cannot be bigger than 5. But we can think about that as 0. So any number between 0 and 5 could be the intersection part. Okay, that's the intersection part. So A, what are the possible values of number of elements in B? We know that this part's number, element number is either 0, 1, 2, 3, 4, or 5 because the number of elements in the intersection part should be between 0 and 5 inclusive. If this is a 0, there's no element in the intersection part. That means they are disjointing. They disjoint. So it's like this, A and B, right? Then how many elements are in B? There are still 3 because this part has a 0 in it. 0 and 3 together, that's 3, right? Then So let me rewrite this with a table. Maybe it's better. So A intersection B, this part in the yellow, we are thinking about the number of elements in it. And let's think about number of elements in B. Okay? If this part here has no element, which means they are disjointing, A and B are disjointing, so there's nothing in it, then think about B only. This part is 0, so together, this part and that part together should be only 3, right?
Mhm.
If there's one element in the intersection part, here, there's only one element, then how many are in B? 1 and 3. So there will be 4 in that element, right? If the intersection part has 2 elements in it, then B will have 2 and 3, so 5. If the intersection part has 3 elements together, so this part and that part together, that's B. Number of elements in B should be 6. For 4, 7. For 5, there are 8. 5 plus 3 is 8, right? But that's the maximum number that we can have in the intersection part, as we wrote here. Does it make sense? That's
Yes.
why the possible values of NB, number of elements in B, is 3, 4, 5, 6, 7, 8. 5. I have numbers here. 3, 4, 5, 6, 7, 8. Does it make sense, Tess?
Yeah, much better.
Okay, Molly. Okay, good. Okay, now part B says if A intersection B is empty, like this one, right? If A intersection B is empty, there's nothing, no elements in it. What is the only possible value for NB? Of course, 3. Right? So even if it's saying that, oh, what if number of elements in A union B is 3? We can find that. Then number of elements in B should be 6. Right? If it's
Yes.
asking, number of elements in A intersection B is 2, what is the possible value for NB? And it should be 5. Okay? Are we good? Okay, then I will move on. The next one is this. Use front end. Front end. Front end means we are estimating, just the first couple digits, 1 or 2 digits. It depends what it says. The first question here is saying you're gonna use the front end estimate with adjustment by rounding to the nearest 100 is needed. So we're gonna look at rounding nearest 100. Looking at this first number, where is the hundredth place?
So that one should be 1300. I think I just misunderstood
Right.
on that. That one I probably don't need reviewed.
Okay. So in this case, it's estimation, so it's not exactly equal. So we're gonna use a squiggle estimation about it's 1300, right? How about this one? This is the hundredth place, and we are looking at the next digit, which is smaller than 5. So that's about what? 60 hundredths, right?
Yes.
Which is 6,000. And here, hundredth place is here. So we are looking at the next digit, which is 9, which is bigger than 5. So we need to round that up. So it's gonna be 2,800.
Gotcha.
Right?
I just did the wrong.
Yeah, I think a lot of students did. So you need to pay extra attention to what you need to round that nearest to.
Okay.
And next one here, 960. So we need to round that up. So it's not close to 900, but it's close to 1000, which is 1000. So you can just add them together. Then you're gonna get this answer. Okay? Yeah, similarly, we can do this one, but we have a little bit different rounding here. Still the front end estimation, but it says round to the nearest 10 as needed. So we are looking at tens place, right? We are underlining all the tens places, and we're gonna do the rounding. So this one next digit is 4, which is less than 4. So it's gonna be close to 310. Next one, 9 is greater than 5, so 450. Next one, greater than 5, so it's gonna be 960. Right? How about this one? 340 or 350?
350.
350. How about the last one?
190.
190. So we can just add them together, then you will have 2,260 there. Okay?
Okay.
Okay, so you can just pay extra attention on that. This one, rewrite each of the following as a base 10 numeral. So because it's saying base 10, maybe it freaked you out, just like base
It
2,
did.
base 5.
And then when I saw the correct answers, it made like way more sense to me. But if you want to explain it to me again, that'd be great.
Yeah, so base 10 is the number that we are using in our number system. Other bases in the questions were like base 2 or base 5. We're not doing that, okay? We're not doing that because I teach that in my method courses because I want you to have some sympathy on your students. They don't know about base 10, even if we are using that. So you need to think about how we regroup. So whenever you have 10 of items, you are regrouping this as one rod, right?
Yeah.
We are doing the same thing for base 2 and base 5. So for base 2, if you have 2 of them, you're gonna exchange that, trade it with one long. So that's
Okay.
what's happening. You don't have to know that for this class, okay?
Okay.
So ignore that, but we know base 10. So whenever you have 10, you're gonna regroup that. So when we are writing, let me give you an example of this number, our number, 2,156. What does this 2 means? It's not 2 actually, right? It's actually 2,000. 2,000 is coming from 2 times 1,000.
Right.
How about 100? That's not 1, but it's 100. 100 is 1 times 100, right? And 5 is not 5, it's 50. So 5 times 10. And the 6 is 6 times 1. So all of these numbers that I multiplied show what the place value each digit is, right?
Right.
But we can rewrite this as 2 times 10 cubed. 1,000 is 10 cubed, and 100 is 1 times 1, 10 to the what square, right? 10 squared is the same as 100, and that 10 is 5 times 10 to the 1 power, and that 1 is 10 to the 0's power. Why do we use 10 to the something power? Because we want to show it is base 10 system. Okay, so this one basically shows you each of the digits place value. So we are given the numbers here to show the place value. 2 times 10 to the 6th power, which means this goes to 10 to the 6th power place. So we know this is 1's place, 10's place, 100's place, 1,000's place, 10,000's place, 100,000's place. That is 10 to the 6th power. So we know that number will be 2.
Okay.
5th power, nothing. 4th power, nothing. How about 3rd power? 6. 2nd power, nothing. Oh, we missed the 1, didn't we? So let me rewrite that again. Okay, I think I have to redo. Okay.
Wait, what did we? 9?
So let's see. This is 10 to the 0th power.
Oh, right.
Because that's 1, right? So starting from there, maybe that's easier. 10 to the 0th power, 10 to the 1's power, 10 to the 2nd power, 10 to the 3rd power, that's hundreds, that's 10,000s. So, and so on and so on, okay? So we're gonna build up from the last one. I think that's easier. So 10 to the 0th power, so 1's place is 9, 10 to the 1's, nothing, 10 to the 2nd, nothing, 10 to the 3rd, that's 1,000's place. So it's gonna be 6,000 up to here, right? And we don't have anything for the 4th, nothing for the 5th, the 6th, we have 2 there. So this is our number. So if I put commas there, it's gonna be 2,006,009.
Got it.
That's the answer. 2,006,009. So you can do the same thing for the next problem here, right?
Yep.
So we can fill that up with that's millions place. Nothing, 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 nothing until you have 1 in the ones place. Okay?
Okay.
Okay. So that makes sense. All right. Let's look at this one. This is really hard to read for you, but I'm pretty sure you have read this question somewhere. So let me just read it, okay? I just copied it, screen capture, so I couldn't make it smaller. Sorry about that, guys. Let me see if I can switch you guys. Yeah, I can't. Okay, anyways, if I just read it, an inspector of weights and measures uses a special set of weights to check the accuracy of scales. Various weights are placed on the scale to check accuracy of any amount from 1 ounce through 15 ounce. What is the fewest number of weights the inspector needs to check all of the ounces from 1 to 15? Okay, so let me draw a picture. Here is a scale. Okay, here is a scale. So there are numbers. We need to check whether it's accurate for 1 ounce. So maybe you can use the weight. This is weight. It tells you 1 ounce, it's exact weight. So you can put that there and check 1 ounce. And if you have 2 ounce weight, you can use that too to check 2 ounce weight and 3 ounce weight, 4 ounce weight. You can do that. However, in that case, it's not fewest number of weights that you can check, because then to check 1 ounce through 15 ounce, you need to have 15 weights, 15 different weights to use, right? So it takes so many weights, but instead of doing that, you can think about power of 2. Power of 2 is very, very powerful. So let me use different color for power of 2 weight. So 2 to the 0th power is the same as 1, right? If you use that ounce, it's still same size and same weight. It's 1 ounce. And for 2 ounces, I can use 2 to the 1 power. So still the same size, okay? 2 ounce. For 3 ounce, I don't need 3 ounce weight because I can just combine these two together. So you don't need 3 ounce, right?
Right.
But you can use 4 ounce. You can still use this one too, but you don't have another one there, right? You
Yeah.
can have only one of them. So you need a 4 ounce scale, which is 2 to the what power? 2 power. 2 to the 0, 2 to the 1, 2 to the 2 power, right? You need a 4 ounce weight to check 4 ounce is correct or not. How about for 5 ounce?
Nope, 4, 6.
For 5 ounce, you can use what we have, this one and that, right? 4 ounce and 1 ounce together is 5 ounce. So you don't need it, right? We can already use this. How about 6 ounce?
Don't need it.
4 ounce and 2 ounce, right? So you don't need it. How about 7 ounce? I can use 1, 2, and 4 together. So 7 ounce, you don't need another 7 ounce, right? How about 8 ounce? We need the 8 ounce because we don't have enough, right? That is actually 2 to the cube. So that's 8 ounce weight you need. How about 9 ounce? Well, 8 ounce and 1 ounce makes 9 ounce, right? If you keep doing that, you all need a lot of different weights, like 3 ounce weight, you don't need it. 5 ounce weight, you don't need it. 9 ounce, you don't need it. 10, you don't need it. 11, you don't need it. 12, you don't need it. And 13, you don't need it because you can use whatever you have. So you actually need only these 4 of the weight to check all of the ounces from 1 to 15. So that's the smallest. You can also think about different, power of base. So for example, if you are doing, well, how about power of 3? Let's try that. If you are doing that, 3 to the 0 power is still 1. So yeah, okay, 1 ounce, we got that. How about 2 ounce? we can't even have that 2 ounce because 3 to the 1's power is 3. We are skipping it. How can we measure, I mean, whether it is accurate or not without 2 ounce? No, we can't. So any other weights cannot measure it. Does it make sense?
Yeah, much.
Okay, so this is the smallest number of weights that you can check each of these, okay? Okay, so he needs what? 1 ounce,
2,
4, 4, 8. That's it, right?
Yep.
So for example, we skipped it, but to check 15 ounce, what can he do? He can use 8 ounce, 4 ounce, and 1 ounce. Is that? Or all together is 15, right? 1, 2, 4, and 8, all together 15. To check 14 ounce, what can he do? Just these 3, right?
Yep.
So 13 ounce. How can you measure 13 ounce? 4, 8 together is 12, and 1 more ounce, 13 ounce, and so on and so on. So you just need these 4 different weights to measure all of the different ounces from 1 to 15, but that's the minimum number.
Okay.
Okay, all right. Yeah, but if you're using different power, you are missing at least one, like 2 ounces or 3 ounces, and so on. Okay, so I think that makes sense now.
Yeah.
All right, this is next problem that I have. Which of the following sets are closed under addition? It says closed under addition. So we talked about closed under addition in the whole number. When we are talking about closed under addition in the whole number, we talked about any number that is in the whole number. So we had really big, infinitely many number set there. So in that case, the whole number was 1, 2, starting from 0, 0, 1, 2, 3, 4, infinitely many, and so on and so on and so on. So it is closed for any whole number because you pick any 2 whole numbers, add them together, it is still whole number. But if we have finite number of set, for example, here, you have only one element there. It's not infinitely many sets, right? So you have only 0 there. So what are the elements in this set B? Only 0. So another element should be also 0 in this set. 0 is the only element. What's 0 plus 0? It's 0. Is that an element of set B? Yes. So it is closed. Okay. How about B? It says set T is the set of 9 times x such that x is a whole number. So I'm looking at part B. So set T is 9 times any number. So we know that all the elements in whole numbers are 0, 1, 2, 3, 4, 5, 6, dot, 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 dot. But our T, set T is 9 times those numbers. What's 9 times 0? 0, 9 times 1, 9, 9 times 2, 18, so multiples of 9. Okay, 36, something like that. Okay, So these are the elements of set T. Now, let's think about whether this is closed under addition. So pick any 2 numbers. 0 plus 9, it's 9, so it is element of T. Let's pick another 2, any 2. How about these 2? 18 and 27 together, what is it? 45? And 45 is actually next number, right? It's multiple of 9. So pick any 2 numbers, then it is still multiple of 9. We can also prove that too. So any number, so let's say that's multiple of 9, so that's 9 times A. Another number, 9 times B. Let's say A and B are not equal. 9A plus 9B, you see that 9 is common factor, so you can factor it out. So however you are adding it, it's always 9 times, which means it's a set of, it's an element of that set. Okay, so it is closed. How about this one? It's natural number now. We are excluding 0, then it's natural number, 1, 2, 3, 4, 5. So pick any number. Like 1 and 1 is 2. Oh, I see that there. How about 2 and 1? 3. 3 is there. Pick any two number and add them together. Is it still in this set? Then yes, it is closed. Let's move on to B. So set B has 7, 9, and 11. Oh, you have only 3 numbers there. So let's pick any two numbers. 7 plus 9. What is it? 16. Is 16 an element of B?
No.
Is 16 an element of set B? No, it's not. So it is not closed. Okay, so this is counter example that makes this statement false. Okay, so this is not true. So not closed. Okay, and I gave you the example there. You can also pick like 7 plus 7 is 14, but 14 is not the element of B. Okay, okay, how about this one? E. Set of something, all elements in X is a whole number and X has to be greater than 8. So if we list this, if we list this set, it's going to be greater than 8, but has to be a whole number. So it's going to be 9, 10, 11, 12, 13, and so on and so on, right? So pick any two numbers and see if it is greater than 8 and it's a whole number.
Okay.
9 and 9, 18. Of course, it is a whole number, it's greater than 8. So pick any two numbers, it's always, when you add them together, it's always greater than 8, right? Okay, so it is closed. F, we have 0 and 1. Guess what? Do you think it's closed or not?
No.
Pick any two numbers, like 0, 0, 0, 1, 1, 1. 0,
Right.
0 is 0, so it is in that set, so it's okay. And 0
Uh,
plus 1 is 1, so it's okay. How about this one? That's
2.
2. The 2 is not the element of that set, right? So because of that, it's not closed. It's not closed. And it says explain why. Why not? You can give this example. 1 plus 1 is 2, but 2 is not the element of that set. Okay, we call that counter example. Okay, are we good? I have, I think, 2 or 3 more. Okay, so let's think about this one. Show that each of the following is true. Give a property of addition to justify each step of your argument. I don't know what steps you are giving there, but I will just give you one example. Well, you can prove it differently too, but you can have some sense of using the property there. So from here, we need to go to z plus x plus y. So I'm examining here. Wow, x plus y was here, but it came to the end, right? So we can have some kind of sense of, oh, must be there was a commutative property, right? But can we do that already? No, not really. So the first thing from here you can do is, let me use different color to show the steps. Okay, so from there, what if I do this way? They are still the same, right? I'm just looking at the left-hand side. I'm not looking at the right-hand side yet, okay? But I need to go to this side eventually. So what did I do here? I didn't change the order, still the same order, x, y, z, x, y, z. But how I associate has been changed, right? So it is associative property of addition. And then, hey, look, x plus y was on the left-hand side, but now it's on the right-hand side. I can just flip this whole thing with z, right? So I can just flip them, commute those two. So I am commuting this part and that part. Do you see how I commute? So it is a commutable property. And then I'm done. I showed you these two are equal. right? I came to that conclusion, z plus x plus y. But I used two different properties there. Make sense?
Mm-hmm.
Okay. Now let's look at the next one. We have x plus y plus z there. And eventually we need to go to y plus x plus z. Now I look at that and I'm going to compare them too. Then I say that, oh, x plus y has been changed to y plus x. And also, how to associate has been changed too. So what would you do first? There should be a lot of different ways. There's not only one answer. But I'm gonna switch these two around first. In order to do that, I need to change that, I need to change that association first. So can I do that? I keep everything the same order, x, y, z, x, y, z, but how I associate has been changed. So I used associative property there, right? And then
Right.
what can I do? I just can flip these two around to go to y, x, and z order, right? So I can flip these two. I am commuting these two numbers. You see that? I just commuted these two numbers. So it's a commutative property. And then to come to that conclusion, I can associate them differently. Y plus x plus z. So I didn't commute anything. It's still order of y, x, and z, y, x, and z. But instead of adding these two first, I'm adding the other two. So it's associative property again.
Okay.
Okay? How do you feel?
I feel better about it now.
Okay, great. Okay, and let's move on to the next one.
My phone might die and I didn't bring a charger, so I'm just gonna listen as long as I can.
Okay. So I'm almost done too. Oh, if you have any further question, you can shoot me an email for that too. In each of the following, determine if the estimate given in parentheses is higher than actual answer or lower than actual answer.
Okay.
So yeah, let's think about this. To get this answer from this multiplication, what did this person do? This is actual, but instead of doing that, this person might have changed that 398 to 400 and multiply that by 500. Then you can have 200,000, right?
Yep.
Yeah, so you increased one of the factors. So for example, think about it. 2 times 3 is 6, but you are increasing that, like 3 times 3. Then it's 9. So the answer here is overestimated, right? So we can think about that. So it should be higher than actual answer because we increased the factor. Make sense? Okay. Now let's think about this one. This one. Okay, division. When you're thinking about division, so let's say something like A divided by B. If you are increasing the dividend, what happens? The quotient will increase too, right? Because you have original number, big number, but you're distributing in the same amount. Then each person gets more if you increase whatever you had at the beginning, right? So you know the relationship. If you are increasing number of people, for example, you have certain number of pizza, but you are increasing more people to distribute, then the quotient will decrease. You just need to know that. So whether you are increasing this or that matters. So for example, that question, let me rewrite that with this one. Instead of doing that to get 10, I think that person did this, 5,000 divided by 500, right? So what happened here is this person decreased decreased this number, but increased this number, right? So decreasing means quotient will go down, right? And he increased this part too, then quotient will go down again. So this one shows lower than actual answer, right? Okay. How about the next one, part C? Let's see. 20,000 divided by, instead of 497, looks like he did 500, right? So what did he do? He increased B. He increased it, but then the actual number, that quotient will go down, right? So it will be lower than actual answer. Okay, how about D? Instead of that number, looks like had 2,000 divided by 200 to get 10. So increased this dividend, so increased one here, dividend, then the quotient will go up, right? And also, this person decreased the dividend, divisor, then the number will go up. So anyway, it will go up, right? Either cases. So yeah, so it is higher than actual value. So you need to think about the number sense for that. Does it make sense, Tess?
Yep.
Yeah, I have one last one here.
Okay.
I think this is for order of operation. Okay. So using the same question, you just need to move around the parentheses to get 1, 134, 5, or 9. So if you calculate this one, 25 minus 3 times 6 plus 2, we know we need to do PEMDAS.
Yep.
Yeah, PEMDAS. So these two, either one from left to right, right? So we see the parentheses here. In the parentheses, it's 8. And then I see multiplication there and the subtraction there. So we need to do this one first. So it's going to be 25 minus 24, which is 1. Right? So it is 1. And it says the first one results from, what's the first one?
130.
I think it's talking about 134 actually, right?
Mm-hmm.
So how can we make 134? Using 25 minus 3 times 6 plus 2. How can we rearrange this? What if we do this way? What do we get? We need to multiply, we need to do inside the parentheses first, right? I already have answers there, but I'm just showing you how you can think about that. You need to have a big number. So if you multiply a big number by 6, you're gonna have a big number very close to that, right? So here we multiply them first, and you get what? 132 plus 2 is 134. So you need to change the parentheses to get 5 or 9. So I will not do all of that. I think you can find that by playing around with the parentheses there.
Mm-hmm.
Okay, that's all I have from the students' work. Do you have any particular question that I want to go over?
Let me see. There was one
Mm.
that I had.
Okay. Let me pause that video.
It was the question, why is an odd number times an odd number always odd? I don't know why this one really confused me.
Oh, okay. So odd number times odd number is always odd number?
Yeah.
Okay. So it is true, because whichever example you bring, like 1 times 3, just give me any odd number, but it's always odd number. But you need to think, when you're proving it, you need to think about the definition of odd number. So even number means it's pairing up, right? So it's always divisible by 2, or it's multiples of 2. Even numbers are multiples of 2. Then what's odd number? it's always one more than odd number or one less than one number,
Okay.
right? So you can define either way. It doesn't matter. It depends on whether you are using that n as a natural number or whole number. It's just difference of that. Okay, so let's say n is our natural number. Then it starts from 1, 2, 3, da, 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 da. So if we plug in 1 there, 2 times 1 minus 1 is 1. So it works, right? So we can define 2n minus 1 as an odd number. So let's have two different odd numbers. So one can be 2m minus 1, and another one can be 2n minus 1, because m and n are different. So both are natural numbers. Does it kind of make sense though?
Mhm.
Yeah, so both are odd numbers. Now let's multiply them. To multiply this, we can do distributive property there, right? So 2m times 2n is 4mn. 2m times negative 1 minus 2m. Minus 1 times 2n minus 2n. Negative 1 times negative 1, positive 1, right? And we can see that all of these that I'm underlining are multiples of 2,
Mhm.
right? So I can factor 2 out. 2 times 2mn makes 4mn. 2 times negative m makes negative 2m. 2 times 1 makes 2n, negative n. And there's 1 left. So in that case, it is also odd number because 2n is even, then 2n minus 1, or 2n plus 1 has to be odd number, right?
Yep.
So yes, if you don't have anything left there, then it will be even number, but because you have even number here,
Mhm.
and you are adding one more to that, that is an odd number.
Okay, perfect.
Okay, anything else?
Nope, that's all I had.
All right, then I think I can stop here and I will share this with everybody else too, okay? Thanks
Thank
for the
you.
participation. Okay, and good luck for the test.
Thank you.
You're welcome. Okay, have a good night.
You too. Bye.
Bye.